Hello everyone! Lab number 6 will cover the topic of nucleophilic substitution reactions. More information on the matter can be found in the textbook in section 19, pages 317 to 320, and section 20 on pages 321 to 326. In the field of chemistry, there are many types of disciplines one can choose to study. Organic chemists are mainly concerned with reactions that form covalent bonds in organic molecules. One type of reaction a chemist can perform in the lab is a nucleophilic substitution reaction. A substitution reaction involves the replacement of an atom or a group of atoms on a substrate for another atom or a group of atoms from an added reagent. Pictured at the top is a typical reaction scheme outlining the substrate and reagents used to form the product along with an undesired byproduct. In a nucleophilic substitution reaction, a sigma bond between the substrate and its leaving group is cleaved, while a new sigma bond is formed between the substrate and a nucleophile, forming the product. Common nucleophiles observed include electron-rich species such as negatively charged carbanions, negatively charged amides, alkoxides, halides, amines, alcohols, etc. In organic chemistry, we consider two types of nucleophilic substitution reactions, SN1 and SN2. When comparing the rates of these two types of reactions, we must consider the concentrations of the starting materials used. In an SN2 reaction, the rate is proportional to the substrate concentrations and the concentration of the nucleophile. This substitution nucleophilic bimolecular reaction is thus deemed the name of SN2. However, if a substitution reaction is deemed to be of type SN1, then the rate of the reaction is only proportional to the substrate concentration. Put another way, we say that the rate is independent of the concentration of the nucleophile. We therefore consider this substitution nucleophilic unimolecular reaction an SN1 reaction. A fair question to ask is, what are the major differences in conditions and substrates for substitution reactions? These guidelines have been previously elucidated over many years of empirical work. Thus, in general, substrates containing primary carbons as the reactive center of a molecule will typically undergo an SN2 reaction, whereas a tertiary carbon will undergo an SN1 reaction. Further, strong nucleophilic species, such as those containing a negative charge, prefer the SN2 type of reaction over the SN1. Also in general, reactions undergoing an SN2 reaction will utilize a polar protic solvent, where SN1 reactions utilize protic solvents and can undergo solvolysis reactions. Other details can be found in the literature and your textbook that relate various conditions and starting materials to the types of nucleophilic substitution reactions which occur. For now, we will focus solely on only one of the two types of reactions. For this lab, we will be focusing on the reactivity of tert-butyl alcohol with the strong acid hydrochloric acid. From this reaction, we expect to form the alkyl halide tert-butyl chloride. This is an example of an SN1 type reaction. When talking about reactions, organic chemists utilize curved arrow notation to depict the motion of electrons interacting with atoms in a molecule. To this end, curved arrow notation is used to depict a reaction mechanism. A mechanism clues a chemist in to the fundamental steps a molecule must pass through in order to reach the product. In this example, we use a full-headed curved arrow to depict a pair of electrons originating from the nucleophile being used to form a sigma bond between two chemical species. Therefore, we too shall use curved arrow notation to describe the mechanism our substrate must go through in order to form the product alkyl halide. In this first step, Our tert-butyl alcohol quickly picks up an acidic proton from hydrochloric acid, forming an oxonium ion species. This oxonium ion slowly loses a molecule of water, forming a tert-butyl carbocation intermediate in solution. Once this intermediate is formed, the remaining halide then performs a nucleophilic attack at the carbocation, forming the product. We note that the rate of this SN1 type reaction depends on the rate of carbocation formation. Thus, if we would like to form our product sooner rather than later, we should choose to use reaction conditions that favor formation of the carbocation. A few notes about our reaction. Tert-butyl alcohol is a polar substrate and is highly soluble in water due to hydrogen bonding. The product, tert-butyl chloride, is not soluble in H2O because it cannot undergo hydrogen bonding with the solvent. Thus, once product formation occurs, tert-butyl chloride is no longer dissolved by the solvent, shifting the reaction equilibrium to the right. Further, we can say that this reaction would not be considered a redox reaction, since we are breaking and forming one sigma bond between a carbon and another atom with a similar electronegativity. That is, an oxygen for a chlorine atom. As an SN1 reaction, the time it takes to form the product depends on the oxonium ion concentration and not on halide ion concentration. Therefore, as mentioned, the easier it is to form the carbocation intermediate, the faster the reaction. Inductive effects caused by neighboring carbons increases the stability of the tertiary carbocation and is reflected in the rate of product formation observed. Generally speaking, for alcohols that undergo an SN1 type mechanism, the reaction rate follows the following trend, where tertiary carbon species undergo reactivity much faster than secondary or primary carbons. Further, the reactivity of halogen acids depends on acidity. However, tertiary alcohols react with any of the three acids, even at room temperature. For this experiment, you will need to procure the following items: 15 milliliters of concentrated hydrochloric acid, 5 milliliters of tert-butyl alcohol, about 10 milliliters of 5% sodium bicarbonate, 15 milliliters of DI water, 1 gram of anhydrous calcium chloride, 3 plastic transfer pipettes, 2 glass Pasteur pipettes, and 2 large test tubes. There is a second half of this lab that involves the purification of our product. For that, you will need a 25 milliliter round bottom flask, Claisen adapter, thermometer, a heating well, and 1 small test tube. Note that, in the lab, both glass and plastic pipettes are available, and one or the other may be recommended or specified, depending on the reagents used. Pictured on the left are 2 glass Pasteur pipettes filled with rubber bulbs. Note that the rubber bulbs can be reused, while the glass pipette is often discarded after rinsing into the glass waste. On the right is a picture of 3 different plastic transfer pipettes. These pipettes are typically rinsed, then discarded after use into the blue barrel waste. To start out, obtain one of the glass test tubes and add 15 milliliters of concentrated hydrochloric acid to the tube using a plastic transfer pipette. Then, add 5 milliliters of tert-butyl alcohol, also using a transfer pipette. Note that the two chemicals may not readily mix and will likely appear as 2 layers. Once both compounds are in the test tube, you may reuse one of the transfer pipettes to mix the reaction mixture using the squirting technique. This entails placing the tip of the pipette under the liquid and drawing the solution into the pipette and squirting it back into the test tube. You will continue to perform this technique for about 15 to 20 minutes. Once done, allow the contents of the tube to settle into 2 layers. The upper layer will be the tert-butyl chloride. If you don't see an upper layer, alert your TA for assistance. Once done, your plastic transfer pipette can be disposed of in the blue waste bin. Once the bilayer can be observed, using a glass Pasteur pipette, remove the lower aqueous layer. You may position the tip of the pipette at the bottom of the test tube and carefully withdraw the bottom aqueous layer. Do remember that this is strong acid and is highly corrosive. Once the acidic layer has been removed, you should be left with impure tert butyl chloride. Add approximately 3 milliliters of DI water to the tube and mix using the squirting technique for about a minute. Then, remove the aqueous layer. You will wash your organic layer 3 times before moving on. With your washed product, carefully add approximately 3 milliliters of 5% sodium bicarbonate, dropwise. You will likely see a significant amount of foaming due to CO2 gas formation. Be careful. Once the bubbling has subsided, mix again using the squirting technique. Then, remove the aqueous layer with the pipette. Like before, you will neutralize the organic layer 3 times. Finally, add approximately 3 milliliters of water and rinse using the squirting technique. Then remove the lower layer. This will remove any trace amounts of base. Once you have finished washing your product, transfer the tert butyl chloride to a dry test tube containing about 1 gram of anhydrous calcium chloride. The calcium chloride will act as a drying agent. Swirl your product in calcium chloride in the test tube for a few seconds. Then, remove the dry liquid via pipette and transfer it to a 25 milliliter round bottom flask. By the end of it, you should have nothing but dry, impure tert butyl chloride in your round bottom flask. In order to purify your compound, you will perform what is called a short path distillation. To assemble this apparatus, you will attach a 25 milliliter round bottom flask to a Claisen adapter fitted with a thermometer adapter and thermometer, and then place your flask in a heating well. And that's it. Unlike the distillation conducted previously, for this lab, you will be collecting your distillate in the crux of the Claisen adapter. All of this should be held at about a 45-degree angle using a clamp and a ring stand. In lieu of the condensing column typically used, it is suggested that you insert into the opening of the Claisen adapter a test tube with a small quantity of cold water or ice to aid in condensation. You will then gently heat your product. Collect the fraction which boils off at 49 to 52 degrees C in the Claisen adapter using a pipette. You should expect to see about 3 or 4 grams of liquid accumulate. With this mass, you can then calculate the percent yield for your reaction. Provided here is an example of a percent yield calculation, presuming a hypothetical 2 grams of product obtained. First, we must calculate the number of moles of substrate used in the reaction. Taking into account the initial volume, which is 5 milliliters, we multiply this value with the density to obtain the grams of substrate. This value, multiplied by the inverse of the molar mass, will give us our amount used in moles, which is 0.05 moles. Compared to the amount of hydrochloric acid used in moles, the alcohol is clearly the limiting reagent in this reaction. Assuming that a 100% conversion of starting material to product occurs, our theoretical yield must then be 0.05 moles. But, alas, with only 2 grams of product collected, we multiply 2 grams with the inverse of the molar mass of tert butyl chloride to find the moles of product, which is 0.0216 moles. The final step of this calculation, then, involves finding the ratio of moles of product divided by the theoretical yield of 0.05 moles times 100. This gives us our percent yield of 43%. Along with the percent yield, you should be able to answer a few other questions about your reaction. Typical examples include, what was the boiling point range of the product? Was your product pure? Also, before running your experiment, it would be best to keep track of the amount of necessary chemicals used in an easy-to-read format. Your TA may ask you to arrange your chemical data in a table format similar to what is seen here. Finally, as with all labs, safety comes first. Therefore, all operations should be performed in the hood. Safety gloves and goggles shall be worn at all times when working in the lab. Of major concern is the concentrated hydrochloric acid, which can cause serious chemical burns and produce hydrochloride vapors. Treat this chemical with extra care and avoid inhaling any fumes. Solid waste for this lab includes used plastic transfer pipettes, which should be placed in the blue trash bin. Halogenated waste consists of any tert butyl chloride product formed. Non-halogenated waste would be any unused tert butyl alcohol. Aqueous waste is any acidic or basic solutions used in the experiment. And last but not least, used Pasteur pipettes should be placed in the glass waste. Another one bites the dust. Thanks for your attention.